Welcome back. The next topic is mathematical analysis of non-recursive algorithms. Recursive and non-recursive. Recursion means the function calling itself. Non-recursion means the algorithm which is very sequential and it's a step by step it moves. In this section we are going to study very systematically, apply the general framework outlined in our earlier section for analyzing the efficiency of the non-recursive algorithms. Let us start with a simple example that demonstrates all the principal steps typically taken in analyzing such algorithms. Consider the problem of finding the value of the largest element in a list of n numbers. For simplicity, we assume that the list is implemented as an array. The following is a simple pseudocode of the standard algorithm for solving the problem. Maximum element of a of 0, 1, 2, 3 up to n minus 1. It determines the value of the largest element in a given array. Input is an array a of 0, 1, 2, 3 up to n minus 1 of real numbers. Output is the value of the largest element in an array. We take Maxwell as a variable to store the a of 0. For I is equal to 1 to n minus 1, if a of I is greater than Maxwell and Maxwell is equal to a of I. At the end we return the Maxwell. The obvious measure of an input size here is the number of elements in a given array, n. The operations that are going to be executed most often are in an algorithm for a loop. There are two operations in the loop's body. The comparison, a of I greater than Maxwell, and an assignment, Maxwell is equal to a of I. Since the comparison is executed on each repetition of the loop and the assignment is not, we should consider the comparison to be the algorithm's basic operation. Note that the number of comparisons will be the same for all values of arrays of size n. Therefore, in terms of this matrix, there is no need to distinguish among the worst, average and best cases here. Let us denote. C of n is the number of times the comparison is executed. The number of times the comparison is executed. It's executed n minus 1 time. So it's easy to compute because it is nothing else but a 1 repeated n minus 1 times. Thus the analyzing the non-recursive algorithm here, the value is going to be n minus 1. That belongs to theta of n. The general plan for analyzing the efficiency of the non-recursive algorithms is decide a particular n indicating the input size, identifying an algorithm's basic operations, check whether the number of times the basic operation is executed depending on the input size. And if it is also depends on the any additional property, the worst case, average case, and if the necessary, the best case efficiencies has to be investigated separately. Set up a sum of expressing the number of times the algorithm's basic operation is executed. Using standard formulas and rules of sum manipulation, either find a closed form formula for the count or at very least establish its order of growth. In particular, we use especially frequently two basic rules of sum manipulations. The sum manipulations are sigma summation of I is equal to 1 to u c into ai, which means c times summation of ai, where I varies from 1 to u. Summation of I is equal to 1 to u ai plus or minus bi, that means summation of ai plus summation of bi. This is what the two summation rules are. The summation of 1 for 1 to u times is equal to u minus 1 plus 1. That means u time. Summation of I is equal to 1 plus 2 up to n is n into n minus n plus 1 divided by 2. It's approximately equal to 1 by 2 n squared, which belongs to theta of n squared. Let's consider the second example, the elements uniqueness problem. Check whether all the elements of the given array are distinct. This problem can be solved by using the straightforward algorithm, that's the unique elements a of 0 to n minus 1. It checks whether all the elements of the given array are distinct. It returns true if all the elements of an array A are distinct and returns false otherwise. You can see the loop here for I is equal to 0 to n minus 2 do, for j is equal to I plus 1 to n minus 1 do. If a of I is equal to a of j, return false, otherwise return true. Natural input size measure here is again the number of elements in the given array n. Since the innermost loop contains a single operation, that's a comparison of the two elements, we should consider it as an algorithm's basic operation. Note, however, that the number of element comparison will depend only on n, but also on whether there are equal elements in the array, and if there are, which array positions they occupy. We will limit our investigations to the worst case only. So by definition, the worst case input in an array for which the number of elements comparisons is the largest among all the array of size n. An inspection of the innermost loop reveals that there are two kinds of the worst case inputs: arrays with no equal inputs, equal elements, and arrays in which the last two elements are the only pair of the equal elements, for which the inputs one comparison is made for each repetition of the innermost loop. For each value of the loop's variable lies between j and its I plus 1, j plus 1, and it is repeated for each value of the outer loop. That's for each value of the loop's variable I between its limits 0 and n minus 2. Accordingly, the C of worst is equal to summation of I equal to 0 I equal to 0 to n minus 2 sigma 1 of j is equal to I plus 1 to n minus 1, the final value what we are going to receive is n minus 1 the whole square minus n minus 2 n minus 1 whole divided by 2, which is nothing but n into n minus 1 divided by 2, that's n squared by 2 equal to theta of n square. That's the C worst of n. So here we conclude how to calculate the time complexity for the non-recursive algorithms. Thank you.